In this video, we're going to look closely at the items within a linear motion system that contribute to finding a point of interest out in 3D space.
The goal of anyone designing a process or piece of equipment is to move an item, inspect a part, or adjust something consistently while duplicating positional performance for as long as possible. First, let's review the differences between accuracy, precision, and repeatability. The accuracy of a linear slide refers to how close it is to a measurement or set true position. It is dependent on a known location for which it must be qualified or calibrated. Repeatability is a term that most often applies for linear motion. It refers to the ability of a system to return to a given location over and over again. Precision applies to the measured range with which a system returns to a position. Consider the comparison to a marksman calibrating a rifle to a target. Hitting a random pattern results in low repeatability and low accuracy. Hitting a very tight pattern is precise and repeatable, but not accurate to a true position. Hitting the bullseye regularly is precise, repeatable, and accurate. When dealing with linear motion applications, the most important factor is typically gaining repeatability within an acceptable, accurate range. Be sure to be realistic when determining the acceptable range of accurate repeatability. Often terms like micron or micro-inch precision are used, or values like 30 micron are set as a requirement for the system. Let's relate real-world positioning to the thickness of the average human hair at about 3.5 thousandths of an inch. The actual width of a micron is like dividing that hair 90 times. In other words, a range of 30 microns would be approximately 1/3 of a human hair. While there are some places in the semiconductor or other ultra-precision fields that require micron positioning, for most applications there's no need to split hairs over microns. So what are the factors that contribute to repeatable and accurate linear motion? First, let's look at the guide rail. A wide array of manufacturers, methods, materials, and specs can result in some misleading conclusions about linear rails. For example, traditional hardened steel shafts or profile guideways are ground to very tight or precise tolerances. This will provide a smooth running surface for the bearing. However, it does not automatically produce accurate, repeatable motion. Most often, these rails are used in parallel. It can be difficult to mount them without special fixtures or laser alignment tools. They also require being mounted on a highly qualified surface. This can be costly, time-consuming, and still produce inconsistency and misalignment. At the other end of the tolerance scale are aluminum rails that are not qualified or machined. They are made to very loose extrusion tolerances. This lack of precision will have a direct effect on the linear motion system being able to achieve consistent repeatability. Many of the slides and guide rails from PBC Linear offer an alternative to these extremes. Using the simultaneous integral milling operation, or SIMO process, precision linear rails can be produced at extrusion level prices. The accurate tolerances held for straightness and flatness eliminate the bow, twist, and warp, and are ideal for most linear motion applications, fitting well with the capabilities of a variety of drive options as discussed later in this video. Often there are factors such as contamination or the operating environment that will have a large impact on the final bearing selection. But whatever style is chosen, the bearings must be able to produce acceptable results within the given location range for an application. Usually this is related to the fit, or how the bearing or carriage feels on the rail. So let's look at the net effect of 4 different styles of bearing on accurate repeatability. First, consider a common choice due to its low price: plastic insert bearings. These typically ride on a loose tolerance, as extruded rail that we discussed earlier. Add to that factors that result in a loose tolerance bearing. Things like plastic is injection molded and not finished machined. Plastic is an insulator that holds heat in the ID of the bearing. It must then be oversized to allow for thermal expansion. The plastic bearing is slipped into a metal housing with only a plastic tab to hold it in place. This can potentially allow for movement of the bearing insert when it's in operation, resulting in a loss of repeatability. Overall, the buildup of tolerances and lack of rigidity put these bearings at the low end of accurate repeatability. Another bearing option is the Freelon Gold plain bearing as found in Simplicity or in the GST carriage of the Simo series. This material is bonded directly to the bearing shell, creating a one-piece bearing. The ID is finish machined to precise tolerances. This type of sliding bearing does require a small amount of clearance between bearing and guide rail to operate properly. Often this is misunderstood to mean there will be play in the system. With no load applied, you can feel this clearance in the bearing fit. In most cases, however, the impact is minimal on the true goal of accurate repeatability at the point of interest. This is because when the bearing or carriage is in a loaded condition, the clearance is removed in the direction of the load. As long as the load is applied during motion, the bearing will provide rigid, consistent performance. While not technically preloaded, in this load-carrying condition, the bearing will perform in a similar fashion. Cam roller type bearings, however, can actually be preloaded and provide rigid, low-friction performance. Preloading removes all the clearance between bearing and raceway and actually applies a small amount of pressure from the bearing. In many of the CRT or cam roller products from PBC Linear, this preload capability is adjustable with a patented side adjust feature. This allows the pressure of the roller on the raceway and the fit of the carriage to be adjusted depending on application needs. For example, camera sliders need very light preload and very low friction movement to achieve smooth, effortless motion. But highly precise measuring applications require greater preload, resulting in greater stiffness and rigidity. Not only is the elimination of play an advantage of preloading, but also minimizing the effects of deflection. Beam or structural deflection will be dealt with later, but first recognize that the components within a bearing system are also subject to deviation dependent on loading. Having the flexibility to spread rollers farther apart and then adjust their preload offers advantages for moment loading situations. For example, compare the difference in deflection between an IVT AAN and an IVT AAQ under the exact same preload and loading conditions. Note that the wider spread of bearings along with the ability to adjust for optimal preload with the eccentric roller results in minimized deflection, stretch, compression of the bearing studs, raceways, and fasteners, translating to increased repeatable accuracy at the point of interest. Remember that no bearing is infinitely stiff. There will always be some give in the material or deflection that will cause loss of precision. The last bearing system to consider is a recirculating ball bearing. This can be either a roundway bearing or a profile rail. These systems are typically very rigid due to being preloaded, but they cannot be easily adjusted. You will often see charts something like this to describe the effect of preload on a ball bearing. The principle of increased preload resulting in higher stiffness is the same as with a cam roller, but in the case of a ball bearing, it must be ordered with a set preload from the factory. The trick is that slightly larger balls are inserted into the bearing raceway to increase the amount of engagement with the shaft or rail.
Rigidity is achieved, but the life of the components will be shortened and premature failures may occur.
One of the biggest areas of concern when evaluating positional repeatability and accuracy is the type of mechanical drive system utilized. Backlash, or the play between moving parts, will have a direct impact on performance.
And the range of specifications from manufacturers will vary widely.
Belt-driven systems, for example, will have some type of variance between the teeth of the belt and the teeth of the pulley. This can result in a cogging effect that produces inconsistent results. Belt stretch and tension can also change over the life of the system, affecting its ability to return to the point of interest.
Because of these variables, belt drives are best suited to high-speed applications that require less accurate repeatability and positioning.
Lead screws can be rolled or ground to very precise tolerances so that their ability to produce repeatable results is mostly dependent on the type of nut. Simple machine nuts will have the most backlash or play, and it will increase as the nuts wear due to their lack of adjustability. A variety of methods have been developed to create an anti-backlash nut. Those with a coil spring and collet mechanism often have good control at installation, but quickly lose stiffness. PBC Linear has developed the constant force nuts to solve the variable clearance problems associated with traditional anti-backlash designs. The constant force nuts utilize a banded spring to provide consistent pressure. This results in equal engagement between the polymer nut and the stainless steel screw for the lifetime of the assembly, and predictable steady drag torque over time while minimizing backlash and play in the system. Any adjustment needed for wear happens automatically as the spring maintains even pressure.
Both lead screws and ball screws offer excellent repeatable performance, with ball screws having the advantage where lower friction and higher efficiencies are needed. Most often they are favored in machine tool applications or where large loads are a factor. Be aware that journal bearings and the retainers used for mounting a lead screw, ball screw, or the pulleys for a belt drive are further components that can introduce play or backlash into a system.
An additional mechanical component in the system often taken for granted is the coupler. Transferring the power from the motor to the screw or drive pulley, this simple item is also subject to backlash that will ultimately have an impact on the positional repeatability of the entire system. If there is a gearbox in between, this is also an item where backlash needs to be considered. There are a couple of items in the electronics area that stand out as having the most impact on positional repeatability. One is the type of motor used. Stepping motors are efficient and cost-effective for many general applications that need to hold a range of positional accuracy within a few thousandths. But the feel of the steps can be magnified in very tight tolerance situations. When highly accurate position is required, a higher cost servo motor can provide better performance. Another thing to consider is how the position is to be measured.
Open loop or non-feedback controllers, when used with stepper motors, are low cost, easy to implement, and can be very accurate. However, the controller assumes that the position of the point of interest sent to the motor is reached, when in reality a motor stall or jam could cause the system to lose repeatable positioning.
Rotary encoders improve quality because a measurement of position is taken, but it is a measurement of motor position and assumes that the mechanical system of bearings, guide, drive components, etc. have no variance or backlash. Linear encoders will provide the highest level of accurate repeatability based on the fact that a measurement is being taken at the point of interest, giving real-time locational feedback. The structure around the linear motion system also comes into play when considering repeatability. First, consider the deflection of the rail or actuator itself.
Bow, twist, and bending dependent on load, the rail's moment of inertia, and location of the carriage along the stroke will have an effect on positioning. Mounting brackets and how a rail, slide, or actuator is held in place also have an effect. For example, T-nuts may be adequate to connect elements in a short stroke or in dual support situations, but for longer stroke or in vertical Y-axis locations,
Additional support gussets may be required to eliminate deflection or a swinging pendulum motion. Keep in mind that various types of applications have different requirements. It may be that a wider range of deflection is acceptable if the motion is slow and there is adequate settling time to account for location. In higher speed applications, it may be necessary to increase the rigidity of the system to shorten the settling time and meet the repeatable positioning required. The last area to consider in a design is not directly related to the linear components themselves, but rather to the target. It is just as critical to consider structure, deflection, and position of the receiving system to ensure that it is in alignment with the linear motion system. Misalignment from the target or misfeeding of items in a process add further complexity to the goal of producing a repeatable process. Remember, when dealing with accurate, repeatable positioning of a linear motion application, each and every component of the system is a contributing factor to achieving the desired result. There are trade-offs based on cost, range of accuracy required, environment, the electronics, surrounding support structure, and other unknown parameters. If you're looking for the right linear motion system to achieve repeatable positioning, PBC Linear has the range of solution to fit the accuracy and budget you require. You can find further product details on pbclinear.com or work with one of our application engineering specialists on your specific application needs.